So this theorem also, this Thevenin theorem also, purpose remains same, whether it is Thevenin theorem, Norton theorem, or any other theorem, is to solve the circuit. DC network circuit is to be solved, and it should be solved in such a manner so that the complexities of the circuit is reduced. Okay, so in this Thevenin theorem also, we reduce the existing network into in a such a manner that we get the simple circuit in which the Ohm's law is applicable. Okay, Ohm's law is the single and simplest mode of representation of the DC network, in which there is one battery source and one load, and V is equal to IR is easily applicable. Okay, so our purpose here in the Thevenin theorem is to reduce the complicated circuit into the circuit in which the Ohm's law is applicable. Okay, so what is the methods which we are adopting to convert the theorem, to convert the existing network into Ohm's law type of network? We will learn here, and what are the assumptions and what is the procedure, both we will understand. Okay, so the circuit is given, a simple circuit is given in your screen. So this theorem provides the mathematical technique for replacing the two terminal network by a voltage source Vt, where Vt is the Thevenin voltage, and resistance RT, which is the Thevenin resistance, which is connected in series. Okay, so some load is given, and this Thevenin resistance, this calculated Thevenin resistance is in series with the battery source, so that the Ohm's law is easily applicable. Okay, so what this Vt is, the Vt is the Thevenin equivalent voltage. It is the open circuit voltage that appears across the load terminals when the load is removed. Okay, so it is also termed as a open circuit voltage. Okay, so whenever the load is there, say resistive load is there, and some suppose this is the part of the resistance, part of the circuit, and some battery source is there, and some resistance, load resistance is connected here. So we have to calculate the open circuit voltage. So this resistance is removed and this circuit is made open. Okay, so this is the open circuit voltage. Okay, so we will derive this theorem and then we will do some numericals as well in the coming classes, so it will be easy. So and result is that we have to calculate the Thevenin resistance of the circuit, given circuit, and we have to calculate the Thevenin voltage, which is the open circuit voltage that appears across the load terminals when it is open. Okay, so first of all, load resistance is removed so that we can get the open circuit. Okay, so when the here the Thevenin resistance is also defined in a simpler manner. So Thevenin equivalent resistance is the resistance of the network looking back into the load terminals. Okay, so whenever the circuit is given and we are having any resistance, few resistance in series, few in parallel, etc. So suppose this is the our load resistance. So when we have to calculate the open circuit voltage or Thevenin voltage, this load is removed. But when we have to calculate the Thevenin resistance, we have to calculate the resistance of the network, whole network, by removing the load resistance and looking into the network. Okay, our plan of action, our the flow of the current will be in the direction from the load into the circuit or back into the circuit. Okay, irrespective of the position or polarity of the voltage source or EMF. Okay, so this is the method, theoretical method of calculating the Thevenin resistance and Thevenin voltage. Now we will do this by a example. Okay, now suppose that this is a network which is given, and also the definition of the Thevenin theorem which we have just explained. It is just for your sake of convenience that it is defined in a easy manner. After deriving this theorem, we will also again define this theorem in a bit complicated manner, or you can say in a refined manner. Okay, so that it is more clear and concise. Suppose that this is the circuit in which this EMF is given. This EMF is denoted by E, and it is having the internal resistance of R. So this internal resistance is placed in series with the battery source. So as I have explained you earlier as well, that either this internal resistance can be positioned below the voltage source or EMF, or it can be above its immaterial, or you can say it is all the same. Okay, so this R1 resistance is given, and this is in series with the EMF, and R2 is given which is in parallel, because in this node there is a current division. If we assume that current is flowing in this manner, then there is a current division which is taking place. Okay, so this is the node, so where the current division will take place. Okay, so and this load resistance RL is given. Okay, so this is the given circuit which we have to solve using Thevenin theorem. Okay, so as to calculate the current which is flowing through the load resistance. Okay, so first thing first, first of all we will calculate the open circuit voltage or Thevenin voltage, and first step is to disconnect the load resistance. So this is our load resistance, and the nodes you can say which are connected to it are this. Okay, so when it is removed, this load resistance is removed, Vt is our open circuit voltage or Thevenin voltage which is to be calculated. Okay, so how it is to be calculated? This is the open circuit voltage. So first of all, we have to calculate the resistance or current flowing in the circuit. So when this load resistance is removed, our current circuit is reduced like this. So here R1 and R2 now becomes in series because this is open circuit. So whenever the open circuit is there, it means that it has infinite resistance. So when it is having infinite resistance, current will not flow from C to A or towards the load because it is open circuit. So the current will follow the path R1, then R2, then internal resistance. Okay, so this is the path which is followed by current. So all the resistance are in series, so we can easily apply Ohm's law to get the current which is flowing from the battery source. Okay, so V is equal to IR, Ohm's law is applied. So voltage is given and the series combination of resistance is given. So we get the current. Okay. So now since the current is known to us, now we will calculate the open circuit voltage or load when load is removed, or you can say Thevenin voltage. So this is the voltage which is appearing. This is the open circuit voltage. So these terminals are parallel. Okay. So, or you can also say that these A and C nodes are same. Okay, because there is nothing further. Okay, it is just shown so that it is clear that between A and B nodes or points once load was connected. So you can say that the voltage across this or the voltage across this is same as they are in parallel. Okay. So what will be the resistance? What will be the voltage across this? It will be IR2. Current is flowing through this resistance. Resistance is R2. So we will get the IR2. So this IR2 will be the open circuit voltage or Thevenin voltage. Okay. So to calculate this, we have current is known to us and we have to just multiply this current with R2 so that we can get this open circuit voltage or Thevenin voltage. Okay, clear? Now we have to calculate the Thevenin resistance. Okay, so what is the step involved to calculate the Thevenin resistance? We have to firstly remove the EMF source and short circuit that. This is the EMF source. EMF is short circuited, so there will be a free flow of current from this branch. And next thing is that we have to load resistance is already removed, so we have to calculate the Thevenin resistance by moving the current, or you can say by looking back into the circuit, looking back into the load network, looking back into the load, which means that the current will flow from the load side towards the network. Okay, so the direction of the current will be this. Okay, so when this is the direction of the current, this is the first node which we encounter. So there will be a current division, and whenever there is a current division, those combinations of circuits or resistance becomes in parallel. And so this R1 and R, this are already in series. So this series combination of R1 plus R will be in parallel combination with R2 as shown in the circuit. Okay, okay, this thing is clear. So our main purpose was to calculate the current which is flowing, or you can say the load current which is flowing in this circuit. Okay, so our purpose was to uh, reduce the complications in the circuit and reduce the circuit into in such a form so that Ohm's law can be directly applied. So we needed Thevenin voltage. In Ohm's law, what we need a voltage source and current, and the current which is flowing through the load or the resistance which are in the series. Okay, that resistance can be one or many, but they should be in series. Okay, so one load resistance is given to us, and rest of the resistances in the circuits are resolved to get the Thevenin resistance. Okay, so to calculate the or to apply this load current formula, we need Thevenin voltage and Thevenin resistance. So first of all, what we have done, we have open circuited the load resistance and calculated the current which is flowing in the circuit. When we are calculating the current in the circuit, we have to look into the polarity of the EMF, and current direction is designed accordingly. Okay, so when we have calculated the current which is flowing in the circuit in different branches, then we have to calculate the Thevenin voltage. Thevenin voltage is the voltage or the open circuit voltage which is across the load resistance. It may be parallel to or based on the current which is flowing. We can calculate the open circuit voltage as we have done here in this case as IR2. So this open circuit voltage will calculate. Then we have to calculate the Thevenin resistance. In Thevenin resistance, what we have done, the load resistance will be absent as earlier, and also the EMF sources will be short circuited. So in here we can calculate the Thevenin resistance. Now, since we are having the Thevenin resistance and the load resistance, Ohm's law is easily applicable and derived as shown. Okay, so now we will define the Thevenin theorem in a more, you can say, refined manner, and then I will also explain you how can you do the same thing in a simpler manner as well. So first of all, Thevenin theorem is the current in any passive circuit elements RL or the load resistance in a network is same as would be obtained if RL were supplied with the voltage source VOC or the open circuit voltage or Thevenin voltage in series with an equivalent resistance RIN, or it can be the internal resistance or the resolved Thevenin resistance. VOC being the open circuit voltage at the terminals from which the RL has been removed, and RT or the Thevenin resistance being the resistance that would be measured at these terminals after all the sources have been removed and each has been replaced by its internal resistance. Okay, so you are not required to mug up this theorem. What you are required to do, you are required to understand what we are doing and what we have derived, and also you can write this theorem in your own words. Okay, you can easily define as that, okay, this theorem gives us the simplified approach to apply the Ohm's law in the circuit, in which the RT is the Thevenin resistance, which is calculated while load resistance is removed, and that resistance is calculated by looking into the circuit, and VOC or VT is the Thevenin voltage, which is calculated as the voltage across the load resistance, and the sources are removed and replaced by its internal resistance. Okay, first of all, we will be taking the simpler problems so that it is clear. Then we will move further for a complicated ones. So this is the circuit which is given here, and in this circuit we have to calculate RT and VT of the circuit, Thevenin resistance and Thevenin voltage. So what we can do is the same what we have derived. We can calculate the Thevenin resistance first or current first, that is up to us. So Thevenin resistance is calculated by removing the load. But if we observe, do we have load here connected between A and B? It is already open circuit. Okay, so the load is not connected here, but Thevenin resistance is to be calculated. So how can we calculate the Thevenin resistance? By looking into the circuit. Okay, into the circuit means, let us assume that A and B was having some load which is removed, so it is open circuit. So current direction will be in. Okay, so current will first move towards the 5 ohm, and in the C node there will be current division. So this 10 ohm resistance and this 10 ohm resistance will be in parallel. Okay, so this is the parallel combination of these 10 ohm resistances, and then this will be in series with the 5 ohm. Okay, clear? So in this way we have calculated the Thevenin resistance. Now we have to calculate the current. So when we are required to calculate the current in this circuit, this voltage source will be active. This 5 ohm resistance may be there or may not be there. It is immaterial because it is later on connected with the open circuit. So current will follow this path and it will not go here because it is open circuit. Whether this is 5 ohm or 0.5 ohm or 50 mega ohm, it is immaterial. Since the open circuit is here, current will not go there. Okay, so 10 ohm plus 10 ohm, 20 ohm. So the current flowing in this circuit will be 0.5 amperes. So current is known to us, resistance is already known to us. So open circuit voltage or the Thevenin voltage will be the same voltage which is across these parallel terminals CD. So it is 5 volts. Okay, is that clear?
Yes, sir.